Period 2. All right, so first scenario looks like this guy's pushing a cart. Here's the description. A person pushes a shopping cart in the store. The energy they push the cart with is 20 joules. Okay, so explain of how it is transferred. You're looking for if energy is changing from an object to a different object, in which case it does, right? 20 joules goes from the person to the cart. Now, if you phrased it differently, that's perfectly fine, but try and compare the gist of what you said with the gist of what I said. Right? 20 joules goes from the person to the cart. It's transferred, changing object, changing place. Explain of how it is transformation. In this case, I wouldn't say there's really any transformation because it goes from kinetic energy to kinetic energy again. Right? So no transformation. Stays kinetic. Okay, stays kinetic. It's kind of nice now looking back at it, having had a little time going through the vocabulary that we can use the vocabulary. Makes it a little easier. But all right, so here, if energy is conserved, 120 joules from the stove should go into 120 joules of thermal energy, right? So electric stove heats up a pot. Right. Pretty much what looks like what it's doing. So 120 joules goes from stove to pot. As I'm going through this, if you can't read it, if I'm, let me know if you guys can see it. So then how's it transformation? It's transformation transforms from electrical energy, right? Transforms from electrical energy to thermal energy. And it's changed type. All right. How about the case of the car? Your 131,760 joules. I'll say that's pretty much where the energy came from. Okay, so put fuel in the car. Okay. I try to be pretty concise with my answers here. Some of you guys kind of writing like pages of stuff. It's just a bunch of fluff. Don't fluff it up. You're putting fuel in a car. That's it. Okay. So, how does it transfer? There's a couple of things you could say. You can say you're transferring energy from the gas pump to the car, or you can say you're transferring energy from the fuel into the actual motion of the car. In this particular diagram, the best you can say is that it goes from the fuel pump to the car. It doesn't really indicate that the car is moving yet or anything like that. It's not using, well, actually, it does say that it's mechanical. So it's already implying that you're burning the fuel and turning it into the motion of the car. So energy transfers from the fuel to the car. Okay, so in other words, you have this tank of gas. The gas is sitting there. When you ignite it, it goes to the actual car moving of the car itself, right? The wheels turning, so on and so forth. You got transformation, transforms from chemical to mechanical. Right. I'll be honest, actually, most likely this is greater. The amount of fuel that you put in is greater than this number, because when you burn the fuel, not 100% of the energy will probably go into moving the car. Where else could that energy go when you burn the fuel? What happens to the engine usually? You ever touch an engine right after it's been running for an hour? Probably not. Why is that? Sure, Ben. It's hot. It's hot. So some of this energy, because you're literally blowing up the fuel, you are igniting it, you're catching it on fire, it gets really hot, and it's expanding. It's a hot expanding gas. Some of it goes to pushing the pistons, which moves your car, but some of it goes into just heating up the engine, right? And that's why you have a radiator. You gotta make sure the engine doesn't get super hot and start melting, you know, stuff in your car. You have fans that blow cool air through the engine so it doesn't get overheat too. So some of that energy is just bleeding away. You're just losing it because it gets hot. Okay, so you actually have some thermal energy here too. Worth noting. Okay, let's move on. So generally speaking, let's see. What do you notice about the amount of energy in both transfer and transformation? If energy is conserved, okay, if energy is conserved, the transferred energy is the same. Okay, what I mean by the same is like, you know, you have the same amount coming out of the object and going into the other object, right? So transfer energy is the same, leaving one object and going into another. Sorry, if you can see that too. Pretty much the same thing for the transformation too. Same for transformation. Same for transformation. Okay. So you, if something loses 20 joules of energy, something doesn't suddenly gain 30 joules of energy. All right. This graph the total energy of the ball as it falls. You'll find that it should be flat. Okay, it should be, right? This is ideal. What we found in our experiment is that you lost a little bit, but that's because of air resistance and stuff that gets away. All right, questions on this page? I want to move on. You gotta hustle. All right, I just want to do a couple of these calculations, just making sure that you guys are able to make these calculations. Here's an example one, right? You take 1/2 times the mass times the square of the velocity. You want to make sure you square this first, and then you multiply, right? So in this case, you have a velocity of 20 meters per second. Okay, so if you square the 20, you'll have 400, and then you do the 1/2 15 times that. That's where they get the 3,000, and we'll do the calculation here. Here you have 30 kilograms. Right? Once again, you want to square the 100, and then you do 1/2 of 30 times the 100. So 1/2 of 30 is 15. 15 times 100 is 1,500. So you have 1,500 joules. Okay? So pretty much that's what you're doing for all of these. When you're calculating these, you just want to make sure you square this one first, and then you do 1/2 times mass times that number. Some of these numbers are really big, some of them are really small. So, any questions on these ones? Okay, they're just practice calculators. All right, this one, some students had issues with. So let's talk about, or actually these two. Can kinetic energy ever be negative? Nope, cannot be negative because you're squaring the velocity. So if you look at the equation 1/2 mv squared, this can never be negative. You can't have a negative mass. And although your velocity can be negative, you know, from the experiment you saw that it was, you know, decreasing height. It was coming closer to the sensor, so it was a negative velocity. You square it. And you can never have a negative number after it was squared. This is also never negative. In other words, it doesn't matter which direction you're moving. As long as you're moving, you have kinetic energy. All right, for this one way you can compare all of these one way you can compare all these is just to do 1/2 mv squared. So if you look at this one, here's 1/2 mv squared, right? Because you have m and v. But this one is going to be 1/2 2m v squared. See how I kind of substituted my 2m for my mass? So if I substitute the 2m for my mass, this actually ends up being mv squared. So which one's going to be bigger, 1/2 mv squared or mv squared? Mv squared is bigger than 1/2. So you kind of use that same analysis all the way through. This one you have 1/2 m 2v squared. I'm substituting the 2v for my v, right? Because it's twice as fast. The speed isn't just v, whatever the number v would be. Say v was 10. That means that you now have a speed of 20. How does that change it? Well, when you square this, you're actually going to get 1/2 m times 4v squared. I don't know if you remember the exponent rules from algebra, but when you square both, right? Because it's 2v times 2v. So 2v times 2v gives you 4v squared, which actually gives you 2mv squared. So this one's even bigger. So actually what it's saying is that when you double your velocity, you end up actually with 4 times as much kinetic energy, which is a big deal. Okay, so just continue on with that kind of thinking, that line of thinking for those other ones. Okay, how about making this calculation? Got an object of mass of 1 kilogram and it's speeding up. So this will be 0.5, this will be 2, 4.5, 8, and 12.5. Okay. If you're not sure how I'm calculating these, I'm just doing 1/2 mv squared for each one of these. Okay, that's all I'm doing. You should get a graph that looks something like this. We'll go 1, 2, 3, 4, 5. Right, 25 divided by, okay. So we'll go up to, well, let's go by 2.5s. That's actually pretty easy. So at 1 meter per second, you have 0.5 joules. That's pretty low. It's about a fifth. At 2 meters per second, you have 2 joules. That's still less than 2.5. Maybe about there. At 3 meters per second, you have 4.5. That's maybe about there. At 4 meters per second, you have 8. Maybe about here. Unless you have this. So if you look at the velocity versus kinetic energy graph, or kinetic energy versus velocity graph, it's quadratic, which should make sense because it's a v squared. It's a quadratic graph. Quadratic. Okay, any questions about kinetic energy? Okay, gravitational potential energy. Notice that in these practice problems, we're using G of 10. Okay, in the lab, you want to use 9.8 because 9.8 is the real world value. In real life, things actually fall closer to 9.8 and not 10. But 10 is a nice round number. When we're making calculations on a test or something like that, and it's just for practice, it makes it quicker. Okay, so we're just going to use 10. Notice that on the gravitational potential energy, when you're calculating this, you have to do it all relative to some reference level. So this object here is 5 meters above my reference level. So I have 2 kilograms the mass times g times that height. This one is resting right at the reference level. It's 0 meters above the reference level. So it has 0 joules of gravitational potential energy. If it is knocked off the edge and it's now kind of falling from there, see how it has fallen 4 meters? You can have a negative 400 joules of gravitational potential energy. You can have negative potential energy. It's negative just because it's just relative. It's all relative. Okay. Lastly, this one, this 15 kilograms, it is 7 meters below the reference level. Okay, so it's not 3, it's 7 because it's 4 and 3. So be careful of that. Okay. All right. Want to go to the last page? Some of you guys kind of had trouble with this one. Number 19. Okay. This is a really good question to know how to answer. Hint, hint, wink, wink. Okay. For this test that's coming up. So, using point D as a reference level, these are a little off. D is supposed to be referring to this line. This is D. This is C. B, A. So that was kind of confusing. The letters are a little off. So from here we want to calculate the gravitational potential energies. So A is the highest or furthest away from point D, or line D, reference level D. It is 7 plus 4 plus 5, which is 16 meters away. Okay, so for this calculation, it will be 1,000 kilograms times 10, which is my G. This is G. And then my H is 16. So this will be 160,000 joules. Okay. Point B will be 110,000 joules. Point C will be 70,000 joules. And point D is 0. Okay. Now this is all if D is my reference level. If I now switch it so that A is my reference level, right here, now my gravitational potential energy is all negative because it's below. It's all below. So at A, that's at the reference level, 0 joules. At B, this would be negative 50,000 joules. C would be negative 90,000 joules. And then lastly, it'll be negative 160,000 joules. Okay. I'm just counting this way. Counting downward. If you plot this out, you essentially get a linear graph. I'm just going to sketch it out. You essentially get a linear graph. It's linear. Any questions about this? I'll put a key up on the Google Drive. Okay, I think there's still some of you guys not really knowing all the resources that are available to you. Okay, Canvas is the place to go. In the calendar, okay, yeah, I'll show you guys what I'm talking about. Because I still have some students saying like, Mr. Mack, I was in class last time. Can I get the sheet of whatever? Or can you tell me what we did last time? And it's like I'm spending all this time setting this information up for you guys. And if you're not using it, well, it makes me feel like I'm wasting my time. Okay, on Canvas, on the calendar, okay, all of this stuff, I have links to all the different files we've been using, all these sheets we've been using. Answer keys are usually up here, review packets. I want to try and start uploading some of the videos that we take in class. It's up here. Okay, so go to Canvas if you're like, oh shoot, I don't remember, or I lost my packet, or what's the answer key, or so on and so forth. The other thing too you can go to is I changed the original page a little bit. Okay, it used to have that file thing up here. I got rid of that. Just use this link. This link goes to class Google Drive. You go to this Google Drive, all the files that we've had in class are here. All of them. Okay, so we've been starting this unit with the energy stuff. Here's the class notes. You can get the notes. See? It's so nice. The notes are here. The lab is here. The two worksheets, the energy park or skate park, and the POGIL. It's all here. Okay, so use the resources. All right. Let's look at the skate park real quick. Okay, so going on to the other packet. skate park. I do. I need a skate park. Yeah. Let's see. So, yeah. It is 8:35. Okay, so the energy skate park, you were to use this fat simulation, right? So if you run it, it looks something like this. You can turn on all these different graphs. The idea here is to see what's happening as the person goes back and forth in real time. Okay? And what I want you guys to notice is a couple things. First, your total energy is constant, right? That is, as long as there's no energy transferring in or out of the system, which is the skateboarder, it can't gain or lose energy. Look at the pie chart. The blue is potential energy. The green is kinetic energy. Keep in mind where the potential energy is the greatest. It's greatest near the top. Oh dang, I got that exactly on. Okay, it's greatest at the top, right? Because his height is the highest. His kinetic energy is the greatest towards the bottom, right? When he is the lowest is where you have it the most transformed. The speed is the greatest. And I think that's important to note because some students kind of get confused. Sometimes they think, okay, well, you're the fastest at the top because it feels like you're going really fast. You can't think of it that way. It is all based on how your energy is transforming. Your energy transforms mostly into kinetic energy at the bottom, and so that must be where you're going the fastest. So you guys are expected to be able to draw these pie charts. All you need to know is the higher you are, the more of your pie chart should be gravitational potential energy. The lower you are, the more of that potential energy turns into kinetic energy. It just kind of switches back and forth. See? Switches back and forth. One other thing I want to point out, look what happens to my pie and the bars as I start at different heights. See, if I start low, I have less energy to start with, and so then I can't go very high. Whereas if I start higher, right, then I can go higher. And the pie chart's bigger, there's more energy there, the bars are taller, right? All of these things are representing where I start represents my total energy, okay? So, that's pretty much what all of this is asking about. Fill in the predictions columns by sketching out what you think the energy pie chart as it goes through 4 points. And you're supposed to create your own track or select one of the pre-made ones. So if you choose, for example, this one, right, the W one, as he goes through, or she goes through, these different positions, right, you're trying to look at what happens to the potential and kinetic energy. So if I compare where he starts, most potential energy, most kinetic energy, maybe half, maybe a fourth potential and 3/4 kinetic, right? The idea here is you should be able to rank where it has the most potential and where it has the most kinetic. All right. Tell you what, I don't want to, I think you guys, I'm getting cues here that you guys fall asleep. So, let me go ahead and hand out the review packets. Keep an eye out. I will upload the keys to everything by the end of the day. But, don't just look at the keys and just copy the answers. I'm not grading this stuff. This stuff is for you to study, so you want to make sure you can do it without knowing the answer, and then you just compare your answer to the correct answer. So I think we got about 20 minutes left of class. I'll just have you guys feel free to work with each other if you want to work by yourself. But you essentially have 3 packets of information to work with. You have the POGIL, there's a lot of information there. The skate park, there's a lot of information there too. And then the review packet I just gave you guys. Use that.